Alrighty, hi everyone. I hope everyone can hear me okay. Welcome to your final review session for your final on Tuesday. I hope that you have been studying and that your finals have been going well so far. This will be a 2-hour review session, and this is recorded and it will go up on YouTube like usual. So I'll send this to Dr. Altimos as soon as I get the Zoom link back from Zoom. I will also be posting a video going through the mock final exam, how I would take the exam, how I would approach each question, how I decide how I want to answer each question. So hopefully that'll give you a little bit of insight in terms of using the answer key. So it'll act like an answer key because I'll show you all the answers as well as like my math, my thought process, and all that stuff. I'll be making this or continuing that after this review session. So that should be up just a little bit after this video goes up as well. I will be posting, I'll send an email out with both video links. It'll probably be this video first and then the review video, or like the final review video, whatever, I guess. Second, I'll just send an email. Dr. Altimos will post it on Canvas, and then it should be there as well under that exams file. I think that's all the announcements I had for y'all. I think that's it. I started writing down what I saw in the I think she should give you an updated grade before the final. She probably has that Monday. I know I've been busy this weekend with stuff and I'm not even a professor, so I'm sure she's just flooded with a couple of things with lab and everything as well. But she should be giving you that before the final as well. So I took note of everything that you've been putting in the chat so far. So I will kind of just go down that list in terms of what's there. I will probably give you just like a brief little background information, just kind of summarize it and give you the important pointers of each of the like topics you talked about. And then we can do like a practice question to see like what that might look like in the final exam. Are there any other questions for me before we begin on anything final related, anything chemistry related, anything like that? Okay. So hopefully this will go smoothly. Alrighty. So the first thing I have written down is combustion analysis. Okay. And can anyone tell me like what combustion analysis is or what that allows us to see? Yeah, so it's kind of like the type of reaction. It also, so this is a type of reaction, I guess I can say. Yeah, awesome. Yep. So the big thing here is that it's going to form CO2 and water. Okay, so the formation of CO2 and H2O is super, super important for combustion analysis. It always is going to be able to tell us what that initial thing that is being burned or being combusted is composed of. So when we look at an example, we can change it so that we have usually a carbon atom and then a number down here, and then a hydrogen and a number down here. And then it reacts with oxygen to produce CO2 and H2O. Okay, so the important thing to note here is that all of the carbon atoms are going to come, or all the carbon atoms that were in your initial product or in initial reactant is only going to be in the carbon dioxide that is formed in your products, as well as all of the hydrogen atoms that are in your initial reactant are going to end up in your H2O product once it's combusted as well. Okay, so we are able to use the information that we get from the carbon dioxide in the water in order to find the information about our starting products. Okay, so we're going to use our products to find out about the reactant. Okay, this can usually be a hydrocarbon. So it's just a carbon and a hydrogen molecule that's being combusted. It can also be a carbon, hydrogen, and oxygen molecule. That gets a little bit more complicated, but we'll just talk about the carbon and hydrogen molecules for right now. Okay, are there any questions just on like the setup of what this kind of reaction looks like? Okay, it's also important to know that this is a gas forming reaction. Okay, so whenever you have a combustion analysis, it's gas forming. Alrighty. Let me just. We'll try a combustion analysis question. For this one. Okay. Okay. So here we have this question. And it's asking for a 1.5 gram sample of hydrocarbon undergoes complete combustion to produce 4.40 grams of CO2 and 2.70 grams of H2O. And I want to know what the empirical formula of this compound is. Yes, this review will be sent out afterwards. And then I don't know if there's a combustion analysis question. I can't remember off the top of my head. But again, the mock final is not the only things that you can ask about. So if it's not, this is still fair game. Okay, so before we work on this question, can someone tell me what an empirical formula is and what does that mean?
Is the empirical formula like related to the molecular formula, kind of?
Yeah, yep. So the empirical and the molecular formula are related, but good, Tia. So the empirical formula is going to be the simplest form. So if we have something where it's like C2H4, this might be the molecular formula, but the empirical formula would be the reduced version of this. So the empirical would be CH2, and this is the empirical. Okay, so we can divide the 2 and the 4 both by 2, so we can get a simpler version of both of them. Okay, so they're related, but so we can have the same empirical formula for multiple compounds, but you can only have one molecular formula for each compound. Okay. Do you want to try this question on our own, or do you want to walk through it together? Together? Okay. If you would like to work it out on your own, just you can mute me for a little bit, and then keep working, or just get started and work ahead of that. Alrighty. Okay, so where's the first thing we need to start at? Our question says a 1.5 gram sample of hydrocarbon undergoes complete combustion to produce carbon dioxide and water. So what should we do first? Good. So
Do
we're
we
going,
have,
go ahead, go ahead.
sorry, I was gonna ask, do we have to figure out like how much is in carbon, how much is in hydrogen, and then like somehow figure out how much is in oxygen or something like that?
Yep, pretty close. So for this one, we don't really care too much about the oxygen just because our initial compound does not have any oxygen in it. So we just need to figure out and need to care about the carbon and the hydrogen this time. So I usually like to write out like a little rough formula of what we're doing. So I always know that I have like CH or C in a number and then H in a number plus oxygen goes to CO2 and H2O. This just helps me because then I can write that I know that I have 4.40 grams of carbon dioxide and 2.70 grams of water. Okay, so we need to do the grams to moles and find the moles of carbon and the moles of hydrogen in each of their respective compounds. So if we're looking at the carbon molecule, we know that we have 4.40 grams of CO2. And in order to get to the moles of carbon, we need to first get to the moles of carbon dioxide. So how do we get from grams to moles here? Yep, we're going to use the molar mass. So 1 mole of CO2 is going to be equal to 44.01 grams of CO2. Right, and we're going to remember in order to change our units, we need to have them on opposite sides of that division sign or that fraction. So the grams is on top in the beginning, so it needs to be on the bottom here. So now we're in moles of CO2, and how many moles of carbon are there in 1 mole of carbon dioxide? Good. So then we know that our molar ratio is 1 mole of CO2 for every 1 mole of carbon. Okay, so we can find out how many moles of carbon are in our CO2. And I got about 0.09. Which we can round to about 0.01. Okay, so now we're going to do the same thing for hydrogen. So go ahead and do that a little bit, and then I'll write that. Excuse me, I'll write that down in a second. Any questions on how we solved for the moles of hydrogen? Did we get a different answer than 3? Makes sense. So what do we do once we find the moles of carbon and the moles of hydrogen? Good, we're going to divide by the smaller one. So keep in mind that when we look back up at our original combustion analysis, all of our carbon came from this guy here and all of our hydrogen came from this guy here. So if we have 1 mole of carbon in our carbon dioxide, that means we have 1 mole of carbon in our initial reactant. So we're going to divide by the smallest number of moles. So we're going to divide by 0.100 moles of carbon, or just by 0.01, or 0.1, excuse me, and then divide by 0.1. So we get carbon equal to 1 and hydrogen equal to 3. Can we use 1 and 3 in our empirical formula? Yes, right? We want whole numbers in our empirical formula. We can't divide, or we can't have like 0.5 or 0.33 of an atom. So we need to have whole numbers. These luckily come out to whole numbers. So we end up with CH3 as our empirical formula. Okay, so this would be the answer for this question. Anyone have any questions on this empirical formula, how we solved it, what this means?
Is there ever going to be a time where it's asking us for like solve for oxygen as well, like CHO or something like that?
Yep, so there could be, yeah, there could be a question like that. So for that one, it would tell you that the compound or the reactant is made up of carbon, hydrogen, and oxygen. And so you would have to find out how many moles of carbon, or so you would find out the moles of carbon and the moles of hydrogen as well. You would then have to use that number of moles to find out how many grams are in, how many grams of carbon is that and how many grams of hydrogen is that. And then based off of the number of grams of your starting reactant, you can sum up the number of grams and the number of carbon and hydrogen, subtract that from the original. That's how many grams of oxygen you have. And then you can use that gram of oxygen to get 2 grams of moles, or to get 2 moles of oxygen. It's a little bit more complicated, takes a little bit more math. If she's going to ask an empirical formula one, I would expect her to probably do a CH one, just because it takes a little bit less time and there's like a big final. So it's just takes a little bit less math. But she thinks she could ask you about the molecular formula. So we'll just kind of talk about that right now. I see some of those questions in the chat as well. Does that make sense?
Yeah, that makes a lot of sense.
Okay. Okay, beautiful. So we could also solve it out for the molecular formula. Can anyone tell me what the molar mass of the CH3 compound is? Yep, so it's about 15.03, I would call it, grams per mole. Okay. So if they were asking for the molecular formula, they would also ask you, or they also give you some information about the molar mass of the compound that's being reacted. So if we said that the molar mass of reacted combusted was 45 grams per mole, how would we solve the molecular formula for this? How would we go about finding the molecular formula? Awesome. So pretty much everyone in the chat so far has said something correct. So we're going to use like a ratio, or kind of find out like how much or how many of these empirical formulas do we need in order to get to the molecular formula. So if we take our 45 and divide it by 15.03, see what the actual number is. We see that it's about 2.994 as our ratio of the molecular formula to the empirical formula. So we can round that up to 3, which means we have 3 times as many empirical formulas as we do molecular formulas. So you can take the subscripts of CH3, because C actually has like a 1 subscript, we just don't show it, and multiply those by 3. So we end up with C3H9. Okay, and this would be our molecular formula. Questions here? Does that help answer the molecular formula questions from above? And then there was a question about the 1.5 gram sample. Here, this doesn't really matter. The 1.5 gram sample would come into play if we had an oxygen in our compound, but because it is a hydrocarbon, we don't need to worry about it for this question. Questions here at all? Yeah, Tia, we'll get to oxidation numbers. We're going to talk about like oil rig and stuff in a little bit. Okay. I then had question 29. So I guess for the people that asked for question 29 or like for questions from the mock exam, do you want to do like general topics first, and then you can go back and look at the video I'm going to post in a little bit with the answer key, or do you want to see that right here, right now with some explanations? If anyone has an opinion. Okay, we'll stick with the general topics then. Alrighty, so let's do percent composition next. Okay. So for percent composition, this is going to talk about how we get to basically the molar mass of the element on the periodic table. So for percent composition, you will always be given elements with different masses. So does anyone know like what those different masses might be, right? If I tell you that you have carbon 12 and you have carbon 13, what do we call those two things? Good. So these are going to be isotopes. So your percent composition is going to be the relative abundance of, I'm sorry, I'm talking about percent abundance here and not percent composition. I'm so sorry. Percent abundance is talking about the isotopes. Okay, so this is going to be that averaged ratio between your different isotopes in your system. Okay, so for this one, you will always be given something where you are like almost close to finding the answer, and you just need to set up the sum of each of the isotopes in its percent abundance and then equal to the molar mass. So if we look at a equation for this, we know that this is the molar mass. And where can we find the molar mass of an element? Good. So this is from the periodic table. This will be equal to the what do I want to call it? It'll be the percent abundance times the mass plus the percent abundance times the mass, and so on and so forth, depending on how many isotopes you have for that sample. Okay. These portions over here will be given in the question, most likely. And you will have to solve for one of those components that you don't know, or you will be given all of the percent abundances and the masses of each of those, and then you'll have to find the molar mass. Okay, any questions there? Okay, so when we plug in a percent abundance to this equation, what form does it have to be in? Does it have to be in the, or can it be in the percent form, or does it, we have to change that? Good. So we have to change this to a decimal. So it has, if we were given something where it was 64%, this has to be changed to 0.64 for our percent abundance. Okay, and then the masses can usually just stay as is. As long as they're in the same units between the same isotopes, that's really all that matters. Okay, any questions so far? Okay. Would you like to see a question for this one as well? Yep, okay. Okay. And I did see Rebecca ask a question about sig figs being important. I don't think so, unless she gives you answers with different sig figs in the multiple choice answer choices. Most of them will have the correct number of sig figs that she's looking for. So you don't need to worry about it too much unless it's like, you know, a question where you have 1.54, 1.5, 1.556. I don't know, something like that where you have to pick from. And that's the only case where those would be important. But for the most part, you shouldn't have to worry too much about them. Use the answer choices to your advantage. Okay, so for this question, we have an element that has a molar mass of 156.34 AMU. I don't know if this actually exists. I just made it up. So one isotope has a mass of 154.36 AMU and is 33.14% abundant. What is the mass of the other isotope? So right, this fake element that I made up has two isotopes. One of them is 154.36 and is 33% abundant. So I'll leave this thing up here a little bit, and we'll try this one on your own. And I'll give you like 3-4 minutes to work on it, and then we'll reconvene. If you're, maybe I can try. If you want to, when you're done, throw your answer choice in the chat, that'll be awesome. And then we can kind of compare. Okay, awesome. So as those answers are coming in, that's also what I got for this. So if you're still working, keep working. I'll kind of start going through how I would go about this. So for this question, I want the blue color. So for this one, we're going to know that our molar mass is going to be 156.34 AMU. And that will be equal to 154.36 AMU times the decimal of 33, which will be 0.3314. Plus our other isotope, we don't know the mass of this one, so that'll be our X. And then how did we get the percent of the other isotope? Good. So, right, we can do either 100 minus 33.14, and we'll get 66.86%. Or we can do 1 minus 0.3314 and still get 0.6686. Either one will work. It gives you the same answer once you convert it. Okay, so this, let's move over here. I guess we'll do. Okay, so then this will be 0.6686 as our percent. So then you can go through and you can multiply the 154.36 times this 0.3314, subtract that from both sides, and then divide by 0.6686. And so then your X becomes 157.32 AMU. A good rule of thumb that I sometimes follow, rather like it gets hard with the sig figs and whatnot, is if your molar mass is given to you with like 3 units or 3 numbers before the decimal point and 2 after, and then one of those isotopes is also given the same way, you can probably solve for your other isotope the same way as well. Just kind of keep it consistent across the board for that one. But again, it's multiple choice, so you don't need to worry too much about it. Okay, any questions on this one here? Be a little bit more comfortable with percent abundance. Alrighty. Now we can talk about percent composition. So for percent composition, this is looking at how much of things are in a compound, right? That seems really big, but we're looking at like stuff, or we can call it, I guess, element, amount of element. Per a compound. Right, so we're looking at how much of one thing is composed of the whole thing, right? So if you took each of your body parts and weighed it off, right? If you chopped your head off and weighed it, that could be like, right, 10 pounds, right? So if you're a 100-pound person and your head weighs 10 pounds, that means that you are 10% of your body weight is composed of your head, right? It's kind of very similar kind of thing like this. This is just using elements instead of body parts. So when we're looking at this, it will usually be given to you where your whole thing or your whole element or whole compound, excuse me, is given to you in grams, you're going to have to convert to moles and then use that molar ratio to find out how many grams of something is contained. And then you can divide by both of them to get your percent composition. So to kind of write that out in terms of what that would look like for a question, you might be given, I guess not that. Um, okay, so we can look at this one here. So in a sample of C2H4O2, what is the percent composition of hydrogen? Okay, so given our entire molecule, we know how much of this is made up of those hydrogen molecules. So can anyone tell me where this question might start out at? What you might have to do first? Okay, good. So let's find the molar mass. What is the molar mass of C2H4O2? Yeah, I got 0.6. So about 60 grams per mole. Okay, what do we do once we have the molar mass? Rebecca, can you explain that a little bit more? I'm not entirely sure what you mean by that. Okay, yes, I understand. I understand that now. So yes, we have to find the total grams of hydrogen and then divide that by the total mass of it. So your total grams of hydrogen is going to be like just this component of that hydrogen. Okay, I understand what you meant now. So you want to find what grams make up your hydrogen component that you're looking for. So if you were to just do 4 times 1.01, we would get 4.04 grams per mole of our hydrogen that's in our sample. So then, like Tia said, we can now do 4 divided by 60 to see what our percent composition is. So we'll do 4.04 grams of hydrogen divided by 60.06 grams of C2H4O2. And what do we get as our decimal? Yep, So does this have any units on it in terms of 0.0672? Awesome. So there's like no units, but you can multiply this by 100 and we can get 6.72%. And so our units here are like the percent symbol and nothing else. Okay, so out of your sample here, 6.72% is hydrogen, okay? Does this make sense? Does 6% or about 7% of your total mass is coming from hydrogen? Does that make sense? And why does it make sense? Why does this seem like a probable thing? Good, right? So out of your samples or out of your compounds that you have here, you have 2 carbon atoms, which are about 12, and 2 oxygen atoms, which are about 16, where your hydrogens are just 4 of that 1. So that's a very, very small element in comparison to the carbon and the oxygen. And so it'll make up a smaller amount of the total mass because it is such a light element. Okay, so that's always something I like to check, right? If you're like, okay, I have C2H4O2 and I get 97% hydrogen. That should set off a little trigger, be like, I might have plugged something wrong into my calculator. So I always like to just give myself a mental check there as well to make sure that I am on the right track. Hey, does this make sense for a percent composition? Yes. Take silence as a good thing. Okay. Okay, let's do our oxidation numbers now. So this will be like oxidation reactions. We'll kind of just go through a little bit with that one. Okay. So when we're looking at oxidation reactions, or I guess we can call them redox reactions, we have 2 components in our redox. What does, I guess I can, this RED portion is going to be our reducing component. And our OX portion is going to be our oxidation. Okay. So there will always be one thing that's being reduced and one thing that's being oxidized. Okay, if we look at our oil rig, as some people like to know, someone tell me what oil stands for here. Good, so oxidation is losing, and what we're losing are those electrons. And then rig over here is going to be reduction, or reducing is gaining. And again, we're gaining those electrons. Okay, so we're always looking at the electron component of redox reactions. Okay, what charge does an electron have? Good, an electron is going to be negative. So if we're losing electrons, should we be getting more positive or more negative? Good, so this will leave you with a more positive. Wow, struggle bus. And your reducing will leave you with a more negative oxidation number. Okay. Questions here? Okay, so let's go over a little bit of like oxidation rules. So can someone oxidation numbers? Can someone tell me a little, any rules or anything that we know about oxidation numbers? What do we know about them? Beautiful, awesome, great job, Lena. Right, so we always know that elements by themselves have an oxidation state of 0, so they'll be equal to 0. So this is elements in their elemental form. So like your transition metals, we think of iron solid, if we think of nickel solid, those will all have a 0 oxidation number. If we think about O2, if we think about N2, F2, right, all of our diatomics, those will also always have a 0 oxidation number because those are in their elemental state. That's how we see them in the wild without anything else, right? Those will always be 0. Okay, anything else we know about oxidation numbers? Good, awesome, Rebecca, I love that one. So the sum of the oxidation So the sum of the oxidation numbers and it is 0 for a neutral atom compound, excuse me. Okay, so if we have something where it's H2O, right? Those oxidation numbers have to add up to 0 because there is no charge on that compound. What if we did have a charge? What would those oxidation numbers have to equal? Yep, if there's a charge, then the sum of the oxidation numbers have to equal that charge. So if there is a charge, oxidation numbers equal the charge. So if you have one of your polyatomic ions, those always have to equal the charge on that polyatomic ion or the charge of that one. Okay, any questions there so far? Alrighty, anything else? I guess a couple things I know is that oxygen always has a -2 when in a compound. And I think those are the big ones to know for that one. Hey, any questions here? Yes, yep, that's also correct. So H is +1 in a compound as well. Yep. It's just if it's so H1 is plus when it's bound to a non-metal. When it's a metal, then it's a -1. So if we have something where it's like NaH, here sodium will have the +1 and hydrogen will be the -1. Yep, and then O is -1 in hydrogen peroxides. So that's when you just have an H and an O in there. So like H2O2. This one here, oxygen is -1 and hydrogen is +1. Yep. Okay, we can go over a couple of these types of questions. Okay, let's look at. Do this question here. I'm gonna try and find a whole thing. Okay, let's try these three. Okay. So when we're looking at the oxidation number of the following, we're going to look at H2O first. So does anyone know what the oxidation numbers are for hydrogen and oxygen here? Good. So hydrogen here will be +1 and oxygen will be -2, right? Going back to our rules, oxygen is always going to be -2 when paired with a non-metal. Hydrogen is a non-metal, so it'll be -2. So if oxygen is equal to -2, then we know that we need something plus X will have to get us equal to 0. So no, we know that X has to be +2. However, we have 2 hydrogens in our thing that must be +2. So if we, each of our hydrogens has to be a +1, because if we divide by 2, then we get a +1 for each of our hydrogens. And so that's why hydrogen is +1. Additionally, hydrogen is paired with a non-metal. And so this means it will always be a +1 as well. Okay, so we have a couple of checks there for that one. Okay, any questions there?
For the oxidation numbers, like, are those just things we're supposed to memorize, or can we figure it out from like looking at the problem?
So for, I guess, oxygen, that's the one you kind of need to memorize, because that one will be -2 when it's in a compound, and then it'll be 0 by itself. And if you know that, then you can kind of use some math in order to figure out the other ones. So you'll see that with B when we go over it right now. If it still doesn't make sense, let me know, and I can kind of explain it a little bit differently if needed.
Okay, thanks.
So when we look at S2O32-, we have 2 elements that we're looking for the oxidation number for. Do we know one right off the bat? Oxygen has to be -2. So oxygen is going to be -2. How many oxygens do we have in this compound? We have 3. So what's the total like charge that oxygen is giving for this one? Good, -6, because we took 2 times -3. Oh, excuse me. We took -2 times 3, and we got a total of -6 as our charge. Okay. So we need our other element to balance out that charge. But what charge should the other element come out to? Good, it needs to be +4. So overall, when we do our -6 plus x, instead of it equaling 0 this time, we have a charge. We need it to equal -2. So if we solve for x, we know that x must be equal to +4. Okay, any questions there so far? So if we look at it kind of going backwards with how we did it for oxygen, we know that we need this to equal to +4, and we have how many sulfur atoms here? We have 2, so that's 2 here. So if we were to solve for that x, or that oxidation number, what is going to be our charge on sulfur? Good, it'll be +2. So x here, +2. So our oxidation state is +2 and -2. Questions there? Okay, if we were to look at this a little bit differently, right? If this was S2O3 and it had no charge on it, right? Oxygen's still going to be -2. So again, oxygen is going to be -2 times 3. So we get -6 as our total charge. We need -6 to add up to 0 because there's no charge on this one now. And so x must be equal to 6. We have 2 sulfur atoms. So we'll take 6 plus 6 is equal to 2 times x. And so x must be +3. So here our sulfur would be a +3 oxidation state. Okay, do we see the difference between those two examples? Take silence as a yes. Okay, and then the last question here is going to be the magnesium and the oxygen going to magnesium oxide. What is going to be our, or does anyone know what the oxidation state of magnesium or oxide is in our reactant side? Good, both of them will be 0. Magnesium is a metal, it's in a solid, so that will be 0. And oxygen is in its O2 gaseous form, so that will also be 0. Okay, so what is going to be oxygen in our magnesium compound? Magnesium oxide compound. Good, it'll be -2. And so what does that make magnesium? Good, +2. We have no charge that we need to, or we have no charge, so that means that our 2 charges must balance out. So since oxygen is -2 and magnesium is only have 1 magnesium, then it must be +2. Alrighty, what questions do we have on oxidation numbers? Okay, great question, Matt. So if we're looking at the magnesium, does magnesium get oxidized or reduced? It's oxidized. This one is oxidized. It ends up positive, so we're losing electrons. And Anna, to answer that one, you don't need to divide by 2 because the 2 is just referring to balancing the equation. And so that one, if you didn't balance the equation, you would still have 2 magnesium oxides. And so that single magnesium oxide component still needs to be balanced itself. So you don't need to worry about the coefficients for these types of questions. Okay, so the magnesium component is oxidized. what about the oxygen? What happened there? Yep, this one is reduced. So which one is the reducing agent? Good. Magnesium is the reducing agent. It is the thing causing the reduction, and so it's the thing being oxidized. Okay, so you have those equal and opposite components. So you have to have, whenever you have an oxidizing reaction, you need to have a reducing agent. If you have a reducing reaction, you need to have an oxidizing agent, right? Those need to pair up together. So, yep, whenever the oxidation state increases, it will be oxidized because you're getting more positive. So if you go from -4 to -2, you got closer to that positive side on the number line. So that's an oxidation reaction. And then therefore the oxidizing agent would be O2. Yep. Okay, if we looked at it this way, which one is your oxidizing agent? What's the oxidizing and reducing agent here? So Rebecca's gonna nail it on the head here. It's gonna be magnesium oxide for both of them. The same oxidation numbers apply. So this is still +2, and this is still -2. This is still 0, and this is still 0. So magnesium this time gets more negative. So this is the thing being reduced. And oxygen is the thing getting more positive. So this is being oxidized. But the magnesium oxide is the only reagent we have. And so that has to act as the agent for both of them to do the reduction and to do the oxidizing. Okay, so for here, the whole compound of magnesium oxide is going to be both of your agents. Does this make sense? Do we feel a bit more comfortable with this? What other questions do we have about oxidation numbers, oxidation and reduction reactions, oil rig in general? What do we think? Feel good? Okay. Okie dokie. Let's see. Okay, let's talk about formal charge and Lewis structures. Yes, Lena. So an oxidizing or reducing agent can only ever be a reactant. And so since MgO was the only reactant in that last example, it has to be it for both. Then you can see that the magnesium is getting reduced and then the oxygen is getting oxidized in here. It contained both in that element or both in that compound. So that's why it acts as the agent for both of them. Really cold. Any other questions here? Okay, so let's look at Lewis structures. So can someone tell me what a Lewis structure is? Cindy, I would only call it the oxidizing agent and not the oxidizing reagent. I don't know if that would still count or not. I've only ever heard it referred to as the oxidizing agent. Yep, Matthew will go over all of this, like the electron geometries, molecular geometries, hybridization, all that kind of stuff with Lewis structures, formal charge. We'll grab all of that. Thanks. So how can we describe a Lewis structure? Good. I like that. So it's a good. Like both of these, I'm going to combine them. So it's a visual representation of bonds between elements, of bonds in a molecule, I guess I'll call it. We can call it the shape of a molecule. All that fun stuff there, okay? Just telling you that like a 3D visualization of this element or this compound, this thing you're working with, okay? So when we talk about a Lewis structure, what has to go in the center of the Lewis structure? What determines that? Good, so the central atom is the least electronegative. So if we're looking at the periodic table, do you like my periodic table? Where is the most electronegative atom? The most electronegative atom. Good, it's the top right. So over here, this is going to be most electronegative. What is our most electronegative atom? Good, I saw that in the question already. Fluorine is our most electronegative. Where's our least electronegative? Nope, hydrogen's still a little electronegative. Where's our least electronegative atom? Good, it's going to be bottom left. This is our least electronegative. And this is francium or FR. Okay, so electronegativity in terms of a trend increases as you go across. And it will decrease as you go down. Okay, any questions on electronegativity? Okay. So the central atom is going to be your least electronegative, and Cindy also pointed out this cannot be hydrogen. Okay, so hydrogen always must go on the outside of your Lewis structure. Okay, so if we were to do an example of, we'll just do CH4 for right now. CH4. What is going to go in the center of our Lewis structure? Good. Carbon's going to go in the center. And then how many bonds are we going to make? Good. We're going to make 4. 1, 2, 3, 4. And then where are we going to put our hydrogens? Yep. And we're going to put hydrogens at the end of those bonds. Lovely. Okay, so when we look at CH4, when we're making that Lewis structure, we want to count how many electrons are in our system. So how many valence electrons does carbon have? Good. And how many valence electrons of hydrogen are there? Beautiful. We have 1 valence electron per hydrogen. We have 4 hydrogens. So times 4, we have a total of 4 electrons from hydrogen. So how many total valence electrons do we have? Yep, we have 8 total valence electrons. When we talk about these bonds here, when we talk about lines, how many electrons are in each line? Beautiful. We're going to have 2 electrons in each of our lines. So if we had 4 bonds and 4 lines, that means we have 4 times 2. So we have 8 total electrons that we used. So we have 8 minus 8 is 0. So we have no charge, no extra electrons. Everything is happy. CH4 is looking happy, just like this. Questions on the Lewis structure? Alrighty, what is the electron domain of this CH4 molecule? Yep. And why is it tetrahedral? How many electron domains are there? Good, there are 4 electron domains. So when we look at the electron domains, we're going to have 1, 2, 3, 4. And so we have 4 total electron domains. What is our molecular geometry for this? Good. Our molecular domain geometry is also tetrahedral because we have 4 bonds. So since we have 4 total bonds, it's going to match our electron domain. We have no lone pairs that are going to change the angles of anything. And so the electron domain and the molecular geometry are the same. Okay. What is our bond angle here? Our bond angle is going to be 109.5. So Dr. Altomos talks about this a little bit in class on Wednesday. And right when we're in a 3D shape, we can get a little bit farther than 90 degrees. So they're actually 109.5 degrees away from each other. So it might look like 90 on your page because it's just a like an XY plane. But here it's actually a 3-dimensional shape. We have to remember that a little bit. And so I think of a tetrahedral as like a tripod almost. So you have like your 3 feet of your tripod where like the phone and the stem stacks up. And then so if you reach that upper portion and like your phone would be that last little bit of your tetrahedral. So your central atom is where the feet connect to the extending portion. And then that would be what the tetrahedral looks like. Then your atoms would be on the outsides of like the feet and where your phone would be usually. Yeah, so Blake, we can definitely go over that as well. So when we look at electron domains and molecular geometries, we can also determine if the the geometry is going to be polar or nonpolar. If we have all bonds and all of the elements that are bonded to that central atom are the same, you will always have a nonpolar bond. If you think about carbon dioxide, what is the molecular, or how many electron domains are there? Beautiful. What's the electron domain geometry? Good, linear. Okay, so you kind of think of this as just an XY or an X-axis going straight across. Your arm is horizontal, right? Your molecular geometry is also going to be linear here. So we have just straight bonds between all of them. Okay, but when we look at this, we can determine if our bonds are going to be polar or non-polar. So what determines if a bond is polar or non-polar? What do we look at there again? Lone pairs, but if we're just looking between like carbon and oxygen, how would we tell if that specific bond, so maybe just this here, how would we tell if that was going to be polar or non-polar? Good, awesome. It's going to be your electronegativity difference. Okay, so bond polarity is determined by electronegativity. So are carbon and oxygen different in electronegativities? Yep, which one's more electronegative? Oxygen is going to be more electronegative. Awesome. So when we draw our dipoles in our or on our Lewis structure, we always point the arrowhead towards the most electronegative atom. So we'll point it, put it in a different color. We'll point it towards the electronegative atom, saying that electrons are going to spend more time near that oxygen atom, leaving our carbon atom a slightly positive, right? If you drew a circle around this, it kind of looks like a positive, like a proton, right? So that positive end will go towards your electropositive atom. So we have that carbon-oxygen bond in red, but then we can also have one in green, right, on this side. The same thing is going to apply. And so we can also draw a dipole that goes this way. Since our dipoles are linear and they're pulling in opposite directions, you can think of this as tug of war, right? If I'm pulling on this pencil, pulling in equal and opposite directions, my pencil doesn't move. And so since our dipoles are even, we have a non-polar molecule with polar bonds. So this one here is a non-polar molecule with polar bonds. Yep, awesome. So then this is the simplest version that we can get for it. But we have on your exam, we had He or XeF4. So if we looked at XeF4, I believe xenon, I don't know, I don't have the periodic table memorized down that far. Is xenon a noble gas? Is it bad that I don't know that? I know fluorine has 7. Okay, so fluorine has 7 valence electrons times 4, so that is 28 valence electrons there. And then xenon has 8, so this will be plus 8 valence electrons. We have a total of 36 electrons. When we draw this Lewis structure, our least electronegative is going to be xenon. So Xe is going to go in the middle. We can then have our 4 bonds for fluorine. And we used 8 electrons there. So we had 36 minus 8. We go back to 28 electrons that we need to put on our Lewis structure. We'll put them to our most electronegative atom first, which is going to be fluorine. And why did I put 6 lone pairs on each of our, or 6 electrons on each of our fluorines? Good, it's going to be the octet rule. When we look at the lone pairs, those are going to count for 1 electron each. So each of the dots represents 1 electron, so that's 6. And then the bond is going to count for 2, so that fluorines now have a full octet. But we have 4 electrons left over. Where can those go? Good, we can put those on xenon. Anything below the 3rd period and below can expand its octet because we have that D subshell and the F subshell for our electrons. So xenon can expand its octet. And so we have a total of 4 valence electrons, or 4 electrons on xenon for 2 lone pairs. So we have a total of 0 charge on our overall in our compound. Okay, so how many electron domains do we have here? Good, we have 6. And their 6 come from 1, 2, 3, 4, 5, 6. What's our electron domain geometry? Good, it's going to be octahedral. What is our molecular geometry? Good, our molecular geometry is square planar. Okay. Let's look at our bonds. Is there an electronegativity difference between fluorine and xenon? EDG is electron domain geometry. Yes, there is an electronegativity difference between xenon and fluorine. Which is more electronegative? Fluorine. So where are we pointing our arrowheads towards? Yep, we're going to point towards fluorine in all of our dipoles. Okay, so if we think about a octahedral shape, this one in my brain reminds me of a like Sims character. So if you have like a little green diamond over their head, right, you have the flat point in the middle, and then you have the 2 points on the outside. So you can kind of think of it as like your piece of paper, and then a point above and a point below that piece of paper. So then in here would be that flat portion of the square, and then points above and below. When we have those 2 lone pairs on xenon, the 2 points, I guess, of your octahedral now become lone pairs. They are in the axial position, going straight up and down. And so if we remove those atoms first and remove that axial position, that creates our lone pairs 180 degrees away from each other. Lone pairs, right, are still electrons. They like to repel each other. They like to be the farthest away from each other. So putting them at the axial position makes them the farthest away that they can get, leaving just our polar molecules of fluorine on that square planar portion. So now you can think of this like a piece of paper where it's a square and you have a fluorine in each of the corners. So now if you pull on that paper in all of your corners, those are all going to be equal and opposite and cancel out. So therefore, these polar bonds make the molecule nonpolar because your diagonals are going to be pulling away from each other in both sides. So overall, even though we have lone pairs and we have polar bonds, they are opposite each other. And so that overall cancels everything out, making the molecule nonpolar. Yes, so if the central atom only had 1 lone pair, now we kind of throw off that whole shape. So that would make the electron domain be 5. And then the lone pair would be, so then our electron domain geometry would be square or trigonal bipyramidal. And then that 1 lone pair would cause it to be seesaw. And seesaw is now polar. Yes, Blake. So if there were only 1 lone pair or 3 lone pairs, then then the shape becomes a little different. And that's going to make everything odd, right? And therefore it would make it polar because nothing is canceling out. We can't put them in different directions in order to cancel them out. Yes, yep, we can know if the molecule is polar based on the shape. Does that help out with a little bit of Lewis structures, with a little bit of electron domain geometries and that stuff there? Okay, let's go over all of our electron domain geometries and all of our molecular geometries. real quick, and then we can, yep, and then we'll do a couple more examples about that as well. Okay, so we have the last couple of things that just came in. We'll talk about nonpolar and polar shapes when we go through electron domain geometries, molecular geometries, and we'll talk about hybridization as well as we go through. Okay, so we can have an electron domain geometry of 2, 3, 4, 5, or 6. So we have 5 total electron domains that we can have. So we can have an electron domain of 2. And then electron domain of 3, electron domain of 4, electron domain of 5, and electron domain of 6. Okay. So if we have an electron domain of 2, we only have one shape that it can ever be. It can either be linear, or I guess the electron domain can only ever be linear. And therefore, the molecular geometry is also going to be linear, because you can only ever have 2 electron domains. Or if you have 2 electron domains, you can't remove one of them and have one, then you just have an element. And that no longer makes like that we don't have that thing. We just have a binary compound there. Okay, so you can either have a linear electron domain or molecular geometry of linear. Questions here so far on what that means? Okay, depending on your bond, this could be a polar or a nonpolar kind of thing. Most likely linear will be nonpolar. Yes, Blake, I can do that. Okay, so this will most likely be nonpolar, just because we think back to CO2, right? This is linear, opposite on both sides. However, if we had something where it was like C bonded to oxygen, bonded to fluorine or something like that, right, even though this is linear, this is still, this is also not a correct Lewis structure, but we're going to go with it for right now, right? If we had something like this where the elements were different on the sides, then that would be a polar molecule. Or I guess maybe a better example would be if we had sulfur, right? If we had sulfur bonded to carbon, which is bonded to oxygen, this would be a polar molecule. Okay, so it's not always going to be nonpolar, but a linear most likely will be polar if the elements are the same on both sides. Questions here? Okay, and then if we had an electron domain geometry of 2, what is going to be our hybridization? What is our hybrid orbital there? Awesome, great job. Yep, this one is going to be SP. When you think of electron domains, you want to have the number of orbitals equal to that electron domain. So since we have 2 electron domains, we need 2 orbitals. The first one will always be S, and the second one will always be P. You can add up to how many P orbitals? Good, you can have 3 P orbitals. And then once you get to 3 P orbitals, what orbital are you going to go to next? Then you go to D, and you can add up to 5 D orbitals, but we only ever really go up to 2. Okay, and you'll see that as we go through the rest of these. Questions on electron domain geometries of 2. Okay, for our electron domain geometry of 3, what is that overall shape that we usually call it? So you determine hybridization based off of the number of electron domains. We'll talk about it a little bit more as we go through this one. Yes, this one is trigonal planar. Okay, so your overarching geometry is going to be trigonal planar. What options for molecular geometries do we have? Good, you can have bent. Or you can have what? Yep, trigonal planar. Excuse me. If we have trigonal planar, how many bonds and how many lone pairs do we have? Good. This will have 3 bonds and 0 lone pairs. What about bent? How many lone pairs and bonds does bent have? Good. It'll have 2 bonds and 1 lone pair. Okay. So if we look at bent and we look at trigonal planar, I'm just going to use like A's and B's here. We can have bent where it would be B, A, and a lone pair here. And trigonal planar will be B, A, and A. I guess I'll use X instead of B, since B is actually an element. Okay. So is bent going to be polar or non-polar? Good. Bent will be polar. What about trigonal planar? Good. This will be non-polar. Okay. You could also have, right, a trigonal planar. We'll call it Z, right? If that other A, if there was 2 A's and 1 Z, even though that this is technically it looks like it's non-polar, that Z would have a different electronegativity, causing it to be polar. Okay, so just because it's trigonal planar doesn't mean it will never be polar, or, oh, I'm sorry, excuse me. Just because it's trigonal planar doesn't mean that it will always be non-polar. There are cases where it can be polar. So you just have to make sure you draw that out a little bit to see it, but most of the time it will be non-polar. Do we see why that changes from non-polar to polar? Okay, awesome. What is our hybridization for electron domain 3? Good. This will be sp2. Hybridization is always based off of the electron domain. And since we have 3 electron domains, that means we have 3 hybrid orbitals that we need to work with. So 1 is going to come from our s orbital, because there's only ever 1 s orbital. And then we need 2 more orbitals. So that's going to come from the p orbital. And so we have a total of 3 hybrid orbitals that'll match the 3 electron domains of the overall system. Yep, and then Patricia, so going back up here, when we look at the, is this a laser pointer? Sweet. So when we look at the X and A one over here, the A's are all the same from the central atom, meaning that their dipoles will all be the same looking out at it, right? So this might be something where it's like, this is the same size as this, which is the same size or the same size as this. Okay. But if we look at the X with the A, and the Z, this one will still have the same dipoles going back and forth, but maybe this one is just a little tiny dipole. And so there's not as much pulling it out in that opposite direction and therefore not canceling it out. So overall, the vectors don't add up or whatever. And so they look different. And so therefore it causes the molecule to be polar. Does that help a little bit? Okay, awesome. Okay. Then we can then have electron domains of 4. For the sake of time, I guess, we know that this one is tetrahedral. And then our molecular geometries. Can either be tetrahedral, trigonal pyramidal, pyramidal, I can't spell, or bent. Okay, questions on those 3 molecular geometries? Okay. So again, kind of using those X's and A's, we can have X in the center and we can have an A, an A, an A, or an A. We can have an A, an A, an A, and a lone pair. Or we can have a lone pair and 2 A's, or two lone pairs and 2 bonds. So looking at this, it's 4 bonds, 0 lone pairs, 3 bonds, 1 lone pair, 2 bonds, 2 lone pairs. Okay. Which ones here are going to be nonpolar? Good, just tetrahedral. So this one is usually nonpolar, and these are generally polar. Or not generally, these will be polar. Okay, and what is your hybridization? Beautiful, sp3. Bent will usually be polar because of lone pairs. Generally, if there's a lone pair, it will be polar, except for that case of the square planar one that we saw. Okay, questions on electron domain 4?
For the third example with the 1x and 2 A's and 2 lone pairs, don't the lone pairs cancel out and all that? And
So no, not for this one here. So if you think of it as like a piece of paper or something with 4 corners, they won't be opposite where like, right, if we have our 4 corners of something, it could be 1, 2, 3, and 4. It won't be opposite where your lone pairs are opposite each other, like 1 and 3. It could be the case where they are in 1 and 4. And so if they're in 1 and 4, that's going to drastically change how the dipoles will work in the 2 and 3 corners, causing it to be polar. So even though it looks like it might cancel out, they're not going to cancel out here.
is it because of like the angle it causes or something? Or
Yep, that's exactly it.
okay. So if it was on corners 1 and 3, then they would cancel off.
Then they would cancel out, but that for bent, that doesn't happen. So bent will bent will always be polar. Good question. Okay, so This one will have 109.5 degrees. This will have less than 109.5, and this will have less than 109.5. This one is about 107, and this one is about 104.5. Forgot up here, but this one here will be 120, and this one here is less than 120, is all you need to know. I'll zoom out so you can see everything I just wrote there. Questions? The ones with lone pairs and non-polar is the square planar, and that's the xenon tetrafluoride that we looked at a couple minutes ago.
Which ones are you saying is like less than 109.5?
The trigonal pyramidal and the bent one.
Okay.
So it's like this angle is less than 109.5, and then this angle is less than 109.5. I don't think she is going to ask for the approximate ones like 107 and 104.5. I think she just wants you to know that it will be less than the typical 109.5 that we talk about for tetrahedral. Good questions around. Anything else with electron domain 5? Or electron domain 4, excuse me. Okay. I will quickly go through 5 and 6, just to leave y'all a couple extra minutes to ask questions about what you have moving forward from here. Okay. So we have electron domain 5. This is going to be trigonal bipyramidal. We have 4 molecular geometries. We will have, I just forgot one of them. You can have trigonal bipyramidal. You can have seesaw. You can have T-shape. Or you can have linear. This one is 5 bonds, 0 lone pairs. This one is 4 bonds, 1 lone pair. This one is 3 bonds, 2 lone pair. And this one is 2 bonds and 3 lone pair. Okay, this looks like this is 1, 2, 3, and 4. This one is nonpolar, polar, polar, and nonpolar. And our hybridization is now sp3d because we need 5 hybrid orbitals. We used 4 from the sp3, and now the next orbital we have to go to is d. Okay, I'll let that sink in, digest. what questions do we have now? Yes. So when we think about the linear one here, the trigonal bipyramidal is going to be a triangle in the center of your like plane. So instead of a piece of paper, you have a triangle as your piece of paper, and then the top and bottom like the octahedral. And then that one will be, so the lone pairs of the linear there will all be in that triangle. So your only atoms will be in that linear portion of the top and the bottom. And so that creates a line. Basically, the lone pairs will cancel out and you just have the line of the dipoles pulling back and forth. Yep. Okay, I will leave you to do electron domain 6 on your own. See if you can find that in your notes, or you can create that up on your own and see if you can determine if they're polar or non-polar. Google has a lot of fun diagrams that look good for electron domain geometry. So if you just look up like octahedral molecular geometry shapes, that'll give you all that information as well. Just so I can answer a couple more questions before 3 o'clock rolls around. I'm sure I'll talk about it in the final exam video as well. So just as a warning, or just as a note, not really a warning. Okay, questions? Any other questions though before? I have no idea about a curve. I do not know. I would assume no, but I don't know. Any other questions? Okay, so let's quickly talk about formal charge and net ionic equations, and then I will let you go. So last thing that you can talk about that deal with Lewis structures is going to be formal charge. And Garrett, there's 40 questions on the final. So formal charge. So formal charge is going to be looking at the lines and the dots. Your lines are going to be your bonds, and your dots are going to be your electron or your lone pairs. Okay. Your formal charge equation is going to be your valence electrons. So if we're looking at oxygen, oxygen is expected to have 6 valence electrons, so a 6 would go in there, minus the sum of the number of bonds, plus the lone pairs. I guess electrons in lone pairs. Okay, so if you have something, or if you have an oxygen atom that looks like this, this oxygen, the formal charge, an oxygen is expected to have 6 valence electrons. It has 2 bonds, and it has 4 electrons in its lone pairs. So its formal charge is equal to 6 minus 6, which is equal to 0. We want formal charge to be equal to 0, unless there is a charge on the molecule. And so your best formal charge will be when all of your formal charges equal to 0, if the atom or the molecule is neutral, or when your most electronegative atom has the like -1 charge on it and equals the charge of your overall molecule. So if you look at something like CO3 minus, CO3 2 minus, excuse me. This is a really good example you can do on your own to see if you can find what the best, or what if Lewis structure would look like for this one. Any questions on formal charge? Okay, looking at net ionic equations. This has to deal with solubility, and the thing looking the same on both sides of the equation. So if you have something where it's Na, let me think. We'll say sodium chloride here. And let me look up the solubility chart real quick. Is it not there? Here we go. Okay, so we'll do sodium chloride and we'll do CaNO3 2. All right, if you had these two compounds together, they will both be aqueous. When you put them and tell them to react, a precipitate will form. It will not be the sodium NaNO3 because this will remain aqueous. Those will always remain soluble. But your calcium chloride will become a precipitate. So if we were to balance this equation real quick, this needs a 2, this needs a 2. So if you wrote out the complete ionic equation, you're going to break up each of your compounds into its ions. So sodium becomes 2 Na plus and 2 calcium minus, or chlorine minus, excuse me. Calcium becomes calcium 2 plus, and nitrate becomes 2 NO3 minus, which goes to 2 Na2 or 2 Na plus and 2 NO3 minus. But because the calcium chloride is solid, we can no longer break that up. And so this has to be calcium chloride solid as well. Okay. So when we look at our net ionic equation, we want to remove any of our spectator ions. So that means anything that looks the same on both sides of the equation. So since sodium looks the same and nitrate looks the same, those will be canceled out. So we'll cancel these out. And the overall chemical or the overall net ionic equation becomes 2 chlorine plus calcium goes to calcium chloride solid. Okay, and this would be your net ionic equation. And you cannot break up a liquid. The only thing you can break up is aqueous. So if you have something like H2O liquid, this is still H2O in your complete ionic equation. You cannot break that up into like oxygens and hydrogens. Gases can also not be broken up. The only thing you can break up is aqueous. Would square pyramidal be polar? Blake, for square pyramidal, if there's a lone pair there, then it would be polar, yes. Okay, and then I guess I can quickly try and do quantum numbers before y'all leave. This will be speedy round. Okay, so for quantum numbers, we have 4 different things that we're looking at. We're looking at N, L, ebb sub L, and ebb sub S. N is going to be your energy level. I had a question about this Navionic equation, the things that we canceled out here. So the sodium and the nitrate, those are spectator ions. So you canceled out spectator ions. Okay. Awesome. So N is going to be your energy level. This can be 1, 2, 3. I guess I'm going to do it this way. N can equal 1, 2, 3, 4, something like that. Okay. So on and so forth. L is going to be your subshell. Okay, so that's going to be your this is going to be your S, P, D, or F, and it will be N-1, or it can be up to N-1, so it can be 0, 1, 2, 3, so forth. M sub L, this is going to be your orbital, and this will be negative L to L. So this can be either 0, -1, 0, 1, -2, -1, 0, 1, 2, and so on and so forth. And then M sub S is just plus or minus 1/2, and that has to deal with the spin of the electron. Okay, only one electron can ever have a quantum number, and all that fun stuff there. Each orbital can only have 2 electrons. So your S orbital has 2 electrons, your P orbital has 6 electrons, your D orbital has 10 electrons, and your F orbital has 14 electrons. Because the S orbital has the S orbital has 1, the S subshell has 1 orbital. This has 3, this has 5, and this has 7. Okay, I hope that makes sense. And I didn't just lose a whole bunch of people. Any last minute quantum number questions? Okay. I think we almost got through everything except for the heat of fusion that I saw, and then like your questions in your mock final questions. So I think it was a good use of our 2 hours. I hope you benefited from this. Again, this video will be posted once I get the link back and upload it to YouTube. I have the mock final that I'll be doing with y'all right above this. So I will post all of my work for the mock final, as well as all of the notes that I took today with that as well. If you have any questions in the meantime, please email me, let me know. I'd be happy to answer any of them. Yep, I'll post them on Canvas. I'll just send them to Dr. Altomos to put like next to the links to the YouTube and stuff and everything. And I'll include it in the email with the links to the YouTube ones as well. I think this is the end of the road for me for seeing y'all, except for on Tuesday. So thank you so much for a wonderful year. I hope you benefited from coming to these sessions if you came to them. I hope you at least enjoyed chemistry a little bit if this is the end of the road for you for chemistry. Good luck with the rest of your endeavors. I hope you have a wonderful time there. If you're continuing with chemistry, good luck with next semester, and OChem if you're continuing with that for those kind of chemistry people as well. Good luck with everything. Please let me know if you have any questions. I've like recommendation letters, just advice of life in general. you have all been really awesome. I'd love to talk to you about your future endeavors as well. I think that's all I have. Good luck. Let me know if you have anything. Thank you all so much. I'm hoping to do that right now for the video. I'm just gonna finish my laundry and then make that. So, or finish that up. So, should probably be later this afternoon. And it will be up on Canvas. Yeah. Yeah, of course. Thank you so much. Thank y'all so much.